my dear students. I hope you all are doing good. It's been many days since I made my last video, so I'm back. So we will continue with this series on vector calculus. So in this video, we are going to introduce vector and scalar fields, which are very important. So most of you already know what the vector and scalar fields are, but let me just explain just for the completeness of this series. So what is a vector field? Right, so you have basically you have to assign, for example, if you are in 2D plane R2, to every point you have to assign a vector. Okay, assign a vector to every point in R2. So what is a vector field? Basically it is a function from R2 to something like this, right? You can have your R2 is x comma y, so you can have something like this x square I plus y xj. Okay, or you can also go to three-dimensional. For example, you can go for R3 to if you have x comma y comma z, then you can go for xy I cap plus x square j cap plus z k cap, something like this. You can even go from R2 to R3, not a problem. What you can do, xy can go to say xi cap plus yj cap plus x plus y k cap, something like this, right? So basically when you assign a vector to every point in your domain, whatever is your domain, right, as we study in functions, that is a vector field. That is a vector field, right? So if I, for example, if I say u is a vector field, that means u has an x component, which can be a function of x, y, z, or whatever are my domain variables, and then it has a y component, and then it has a z component. So that is the idea of a vector field, right? So we can see that whenever you have, a motion, so we have velocity field. At every point of the motion, we have a velocity vector. So that is a velocity vector field, right? So that is a vector field, right? Now what about scalar fields? Scalar fields are simple. They are the functions, right? To every point in your domain, to every point in your domain, you assign a scalar quantity. Scalar quantity, that is your scalar field. That is your scalar field. Right? For example, can you think of an example of a scalar field? For example, if we have to every, this is your square plate, metal plate, at every point you are assigning temperature. So temperature is not a vector quantity, it is a scalar quantity. So this is going to be a scalar field, right? So we already are familiar with scalar fields. So vector fields are new to us. We already know what to do with scalar field. For example, if you have f from R2 to R3, that is a scalar field, so it would be something like xy. So this will be, because this is a scalar quantity, so you will always go from your domain to R, because scalar quantity means a real number, right? It can be a complex number also, but right now we will deal just with real numbers. So we are saying that to every point in your domain you are assigning a real number. So this will always go from R2 to R or R3 to R, wherever you are, right? So your domain, so your scalar field is a function from your domain to set of real numbers. So this you have to understand, right? So we already know, like if you have a function, so it will be something like this, f of x comma y comma z. So we already know, if you have a function, how to deal with derivatives and all those things. But for vector field, we have a vector. So we already have done many things in this series about how to differentiate these vectors and find the curvature, torsion, and all those things we have already done. We'll be doing something else also, like divergence, gradient, and we'll apply Laplacian operator on vector fields. That we'll be doing in the next videos. So in this video I would like to give you some examples of vector fields. So look at this example of vector field, so that you have an idea. So here I have this vector field I cap plus j cap. So f of x is I cap plus j cap. So basically I am from R2 to going to R2, that is again a vector in R2. So every point x comma y, whatever is the point, I don't care, is going to the single constant vector I plus j. So can you see at every point this is I plus j means having slope 45 degree, magnitude 1. So can you see that at every point I'll just draw the same vector, same direction, same magnitude. So that is a constant vector field. Does that make sense? So now you can imagine like how you have to, this is your vector field, right? Okay, so let us look at another one. Look at this one. Here again from R2 to R2 we are going. R2 to R2. Our field is from R2 to R2. But this time we don't have a constant vector field. So what we are doing here is you have x comma y and then you are going to yi cap minus xj cap, right? So for example, if I am at this point, right, this point is x is 1, y is 0. So I am going to 0 I cap minus 1 j cap. So I am going to minus j cap. So this is a unit vector in the opposite direction of y-axis. So can you see like this? And if I am at this point which is 0 comma 1, then I am going to 1 I cap minus 0 j cap. So I am going to I cap. So can you see this is I cap, right? And similarly if I am at this point which is minus 1 comma 0, minus 1 comma 0, then I am at 0 I cap plus 1 j cap, 1 j cap. So here it is. Can you see? Does that make sense? So this is this kind of vector field. So at every point you have to stand and you have to see what is the vector and then you have to draw that vector. And then we have a famous vector field which is called inverse square vector field, which is there in magnetic fields, gravitational fields and so on. So I think everybody is familiar. So we have this famous, let me write down, inverse square vector field. Inverse square vector field, right? So what is this vector field? This vector field looks like this, that you go from r cube, at 0 it is not defined, r cube minus 0, okay, so you skip 0, you'll just know in a moment why, to r cube, something like this. This is a function that f of x comma y comma z equal to c upon mod of r cube into r vector, right? Where r vector is your position vector, x I cap plus y j cap plus z k cap. So do you remember this is a famous, we have this formula in magnetic fields also and electrostatic field also, and then gravitational forces are also, governed by this vector field, right? Now somebody can ask that why this is called square, because here you have a cube, right? So it's because you can write it like this, c upon mod of r square into r cap upon mod of r cap. Now this is a unit vector, right? So then this is going to the magnitude. So that is why this is inverse square, because this is the position, like magnitude of the position vector. So how far you are from the origin, okay? So your potential is inversely proportional to the square of that magnitude. That is why it is called inverse square vector field. Does that make sense? And if you try to draw it, this is how it is, right? So if you are at any point, then you have to just see that this is a function of r only, right? So if you are on, for example, a constant r, the vectors are going to be, same. Can you see? Depending on the position vector, obviously, the direction will change, depending on the position vector. Okay, so this is all about vector fields. And in the next videos, we'll be talking about how do we calculate the divergence, convergence, and we operate Laplacian operator on vector fields, and what are their physical significance. Thank you for watching this video. Please share this video and subscribe to this channel. Keep supporting, and if you have any doubts, write in the comment box. Happy learning.